how can we visualize a complex function? So a function that takes a complex number as an input and a complex number as an output. What are the visual and analytic geometric tools that we might have at our disposal to help us illuminate the algebraic properties of that complex function using geometric visual insights? So strap in, because this perspective that we're going to take on geometric properties of complex functions is essential to the correspondence we're building, this Plan B idea that thinking algebraically about complex functions and thinking geometrically are important in their own right, but what's more important than them individually is how they come together and how we can use our geometric understandings to help inform our algebraic understandings and vice versa. So, the key to this, in our previous video, we talked about how a complex function determines a pair of real valued functions, u of x and y, v of x and y. We call them the real and the imaginary parts of the complex function. And because of that, because we can see a complex number as a point in the complex plane, and the complex plane is an awful lot like the real Euclidean xy plane, right? We can also think of a complex function as a transformation of the xy plane, just by forgetting the fact that my complex number x plus iy has this complex arithmetic structure and just treating it as an ordered pair x comma y. And then transforming that ordered pair x comma y according to the functions u and v, which are the real and imaginary parts of a complex function. That erases the i's completely from the function and lets us treat it as just a real transformation of the real plane. So here's an example of what that might look like. If I have the function f of z equals z squared, the complex squaring map, right? I can feed an input, say 2 plus I, into that function, and I can evaluate f of 2 plus I by treating 2 plus I as a complex number and just squaring it, right? Using the squaring arithmetic that we know from complex numbers. 2 plus I, the quantity squared, FOIL it out, right? And then remember at the end of the day that I squared is equal to -1, which allows me to simplify to 3 plus 4i. So that's what it looks like to do this using complex arithmetic. But from the real perspective, what I would just do is I would take the input 2 plus I, forget that it's a complex number, and just treat it like an ordered pair. Right? Treat it like it's the ordered pair 2 comma 1. And then I would need to be plugging in 2 comma 1 into the real part function, which when we find the real part of the squaring function f of x plus iy equals x plus iy squared, the real part is x squared minus y squared, and the imaginary part is 2xy. And so I would just be plugging x equals 2 and y equals 1 into the real part function and into the imaginary part function separately. And if I do that, we get the predictable result, right? That x squared minus y squared, the real part, for x equals 2 and y equals 1 evaluates to 3, and 2xy evaluates to 4. And that just happens to exactly agree with the real and the imaginary parts that we got when we evaluated this as a complex function. So you might look at these two evaluations and say, well, clearly evaluating it as a complex function is a lot simpler. And I would agree with you, right? But evaluating it as a real function is what gives us the entree into treating complex functions like transformations of the real xy plane, which is going to give us a way to help visualize them. And so, yeah, it's harder to do it algebraically as a real valued transformation, but geometrically, it's the real valued functions that enable our visualization. So how can we visualize a complex function? First of all, it's worth thinking about what the graph of a complex function would have to be. So when we study functions in the secondary curriculum, functions whose inputs and outputs are real numbers, well, what does the real number line look like? It's just a line, right? And so if my input lies on a real number line, my output is also going to lie on a real number line. And to visualize the function, the relationship between input and output, what we just do is we take the output, we put it perpendicular to the input, we get an x-axis, we get a y-axis, and we can plot those points for which the y-coordinate is f of the x-coordinate, right? And so the graph of a real valued function of a single variable lives in a two real dimensional vector space, the xy plane, right? So the graph is a subset of the xy plane because we need one dimension to record the inputs and we need one dimension to record the outputs. And that's what the secondary curriculum does, right? That's its main analytic geometric correspondence between algebraic properties of real functions and geometric properties of the graphs of real functions, which are subsets, usually lines or curves, inside of the xy plane. So what would that have to look like on the complex side? Well, anytime we use the word graph of a function, right, as I mentioned before, we need one sort of geometrical set of dimensions to record the inputs of that function, we need a whole second set of geometrical dimensions to record the outputs. And so the graph is going to live in what we would call the Cartesian product of those domain and codomain spaces. So for a real valued function, the graph is a subset of the Cartesian product of the real numbers with the real numbers, which is the two-dimensional real plane. But for the complex numbers, the graph of a complex function whose inputs and outputs are both complex would have to reside in the Cartesian product of the complex numbers with itself. We need to keep track of a complex number input and a complex number output. And that would be two-dimensional as a complex dimension. But because each complex dimension has a real and imaginary real parts, that would make this a four-dimensional real vector space. If I wanted to really visualize what the graph of a complex function looks like using real vector spaces, we would need a four-dimensional real vector space. And that's just not something that we're very well equipped to think about geometrically. There are ways, but they're not usually ways that we like very much. So using just purely the graph of a complex function is not going to be our way in to visualization. Instead, we're going to have a different idea, a better idea, a way for us to keep track of the inputs and the outputs, not by taking a Cartesian product of the two and increasing the dimension up to 4 real dimensions, but instead taking the inputs and the outputs and just kind of either putting them side by side on the same screen or the same piece of paper, or because the inputs and outputs are both subsets of the same complex plane, we could just overlap them. Right? Take the inputs and the outputs and visualize them both on the same complex plane. That's probably going to be the most efficient way of doing this visualization. And so that's what we're going to do. For a complex function w equals f of z, we're going to plot both z and w, both the input and the output, on the same copy of the complex plane. So what might that look like? So here's an example of a complex function. The function w equals 1 minus z over 1 plus z. Right? We're going to call this type of function a Mobius transformation in our next video. But just taken as an example of a complex function whose input is a complex number z and whose output is the ratio of 1 minus z over 1 plus z. One way of visualizing this function is just by going one point at a time. For these input values z, we can see what the output values w look like. And just by moving this point z around, we sort of get a sense of how this function is turning one point in the complex plane into a different point, potentially, in the complex plane. This allows us to do things, for example, like maybe we can find a place where z and w exactly overlap. Looks like right about here. This would be a point for which f of z is equal to z, right? So there's an algebraic connection. If we can figure out what this point is, we would call that a fixed point of the transformation. We can also use this to do things like figure out where is f of z equal to 0, right? So when z is equal to 1, in this case, f of z is equal to 0, and so we can use this graphical insight to figure out zeros of my complex function. And we can also kind of, in this example, get a sense of when are the inputs relatively small in modulus, when are they relatively close to the origin. So it looks like the further my input gets away from the origin, the closer my output gets to the complex number -1, it looks like, right? That's almost like an asymptotic observation. And also, the closer that my input gets to -1 in the complex plane, it looks like that makes my output want to run away. That's kind of like a vertical asymptote in a way from the secondary curriculum for real functions, right? When my input gets close to -1, my output tends to run away from the origin out to the fringes of the complex plane. So this is sort of an initial way of visualizing, and it's not just visual, it's also tactile, it's also kinesthetic. So what you're going to notice this week is that we're going to use a lot of these kinds of interactive tools to help to build our geometric reasoning, our geometric intuition. Again, kind of hitting various different learning style preferences all at the same time, which is the best thing to do with the concept of learning styles, right, is to try and design experiences that can hit multiple of those different modes. Where here we're hitting visual, we're hitting sort of kinesthetic and tactile because I'm playing around with this tool and observing what's happening. Right? And so this is kind of as close as we're going to get to a graph of a complex function. It's a transformation, right? It shows us the relationship between input and output because we're plotting both of those input and output points on the same complex plane. The thing we can't really do is what we did in real functions, which is to look at the entirety of possible inputs and relate those to their corresponding outputs. That requires kind of more dimensions than we have the space to do here. But in our next video, I do want to look at maybe some additional geometric tools that can help us to unlock some more insights about how transformations defined by complex functions can transform things like straight lines and circles and areas and squares and polygons and things like that. So that's what we're going to look at in our next and last video for this introductory portion.